So a quick recap of our data structures chapter so far. We've learned about lists, and we learned that lists are mutable. We learned about strings that behave like lists, and we learned that that's immutable. We learned about tuples or tuples, and those are both also immutable. We saw that strings can only hold text, but lists and tuples can hold any type of value. In this video, we'll show you that any type of value even includes other lists. So if I have a list, the elements within that list could be lists themselves. These nested lists, or multidimensional lists, can be useful for representing a lot of data in the real world. For example, building matrices, or game boards, or grouping elements into subgroups within some larger collection. In Python, we can create nested lists using literals as we would with regular lists. So I can create some variable, I'll call it nested list equals, and then I could put a list in there, 1, 2, 3. Or if I wanted, I could wrap that list in another list. So a second set of square brackets, and then a set of higher level commas. And then we'll say 4, 5, 6 as a second item in the top level list. And I can say 7, 8, 9. So notice that's a list of lists. We have the list 1, 2, 3 as the first element in this larger list that contains 3 other lists. So I could say, what's the length of my variable nested list? And notice it didn't say 9, even though there are 9 total integers in there. It said 3, because at the top level, there are 3 lists. There are 3 elements in that top level list. If I say nested list at 0, so grabbing the value at the first index, that whole thing is itself a list. If I say nested list at 1, it's the next item in our top level list. On the other hand, if I say nested list at 1 at 2, that is to say provide 2 indices, each with their own set of square brackets, that accesses a single item from one of the lower level lists. A way of looking at this is that's the same as saying nested list at 1 in brackets, and then taking the result of that and accessing that at index 2. Right? So the result of nested list at 1 is this list. If we say that at 2, it says grab item from index 2 from that sublist. Note if I use membership and say is 3 in nested list, that's false, because again the items of nested list are the list items, so none of those are the number 3. But if I say is 3 in nested list 0, which is itself a list, that's true because the items in there are 1, 2, and 3. To get a sense of what's happening with nested lists, when we make a nested list, we get something like depicted in this image here. So the variable, in this case list2d, contains a reference which points to a list somewhere in memory. But the list it's pointing to in memory is itself storing references, or remember these are just addresses, to another spot in memory, where the items, or the lower level lists, are being held. So at the top level we have a reference to a list, and the elements in that list are themselves references to smaller lists. This is called a two-dimensional list. You can think of this like a grid. It has columns and rows like in a grid or a matrix. And to specify a single cell of that matrix, we need to provide both a row and a column index. Now a row in this design is one of the lower lists, so ABC or DEF, and the whole grid itself is a list of rows. So if I wanted to access a single cell from that grid, I would have to provide 2 indices, one for the row and one for the column. But the question is, which one would come first? Do I provide the row index first or the column index first? So for example, if I access this variable at index 1, 0, so I said list2d square bracket 1 square bracket 0, is that 1 is the first index there, referencing the row or the column. So I say list2d at 1, so that goes into this variable here, which notice that's pointing at which row we're looking at. So the first index is the row index. And then I have a second index, which in this case I said was 0, and that tells me which of these values, so which column I want to extract from that row. So returning to our example, if I said nested list at 2 and at 1, if this is our nested list, so these are the 3 rows, and the columns are the individual values in those rows. So we have one column that would be 1, 4, 7, another column that would be 2, 5, 8, etc. So if I say nested list at 2, 1, that says go into row 2, column 1. So row 0, 1, 2, and then column 0, 1. So if I say nested list 2, 1, I should get the value 8. So let's apply this new knowledge and solve a programming task that says write a function that accepts a nested list as an argument and prints the elements of each sublist on a separate row. So if we're given some nested list like 1, 2, 3, 4, 5, 6, 7, 8, it will print out one row, then the next row, and then the next row. Notice even though I say these two-dimensional lists have a grid-like structure, in a grid you tend to assume that for each row the same number of columns exist. But in a 2D list that's not necessarily the case. We can have what are known as ragged lists. That is to say, a list that has many sublists that are of unequal size. So in this case we have 2 that are of size 3 and 1 that's of size 2. So this task asks us to traverse our nested list, printing one row at a time. So let's make a new file. We'll call it nestedlists.py. Here I'll say def print 2D list, which was the name of our function from the challenge, and that takes in some two-dimensional list. Let's call this lis. Now if the goal is to just traverse and print the items in our list, we just need a loop. So I'll say for I in range len of list, and I'll say print list at I. Let's set up our code so we can run this, def mains, and that says print 2D list with the input, and I'll just use the one from the problem itself, 1, 2, 3, 4, 5, 6, 7, 8. Notice the colored brackets in the IDE are a great benefit in this situation. It is very easy to lose track of which opening and closing brackets you've typed and which ones you haven't, but having the colors definitely helps you align that visually. Since this is printing, we don't need to print any results, so let's just run our main, save and test. Oops. Bring this down. Exit and clear. So if I go to Python for nestedlist.py, we run our code, and it kind of works, but this isn't what we were aiming for. Instead of printing out the values, it printed out the whole blocks of lists. If we go back to our task, notice it doesn't have any of the list formatting, it just wants the values in our output. So let's see if we can't break this problem down in a bit more nuance and print just the values for each row. So the loop we have now goes through the top level list and prints out each item. So this is going through each row. So I'll say for each row, we're printing out each item, but instead we want to now for each one of those rows go for each item. So we need a second loop that traverses those inner lists as well. So we'll say for j in range len of list I. Before I fix the next line, a couple things I want to point out here. It's important you don't use the same index as your outer loop. So if we have nested loops, we always want to have different indices. Otherwise, we'll lose track of which one is which. And a common convention, since the outer loop is already using the index I, is to just use the next letter in the alphabet, so J in this case. Another thing I'd like to point out is the range of this loop is not going for the entire list, but it's accessing the inner item, so whatever row we're currently on, list at I is one of those sublists, and it's saying for the length of that sublist, take each index. Now, if that's the case, we're going to print that out, so we'll say print list at I, J. So what we had before prints the entire row, now it's just going to print a single value. Let's save, test this out. Well, we got rid of the list formatting and we're printing all the values, but we're not getting them in that grid format the way we wanted. So the first row needs to be one line, the second row needs to be the second line, the third row should be its own line. Having each individual item on its own line is not what we were aiming for. So the issue here is that every time we say print, it includes a new line at the end of that. So instead of printing each value, let's build up each row and then we'll print the row once it's complete. So say at the top of each row, say for each item in row. Now at the top of each row, we'll just make an output variable, call it output, and this is going to be printed, so it's going to be some string. It starts empty, and then each time through our loop, we'll take this value that we're printing, and instead of printing it right away, which includes a new line, we'll take that and add it to output. So I'll say output plus equals the string of list at j. Since these might be numbers, we don't want to try concatenating a bunch of numbers into a string, so let's convert it to a string, and then we'll concatenate those. So that says we've gone through each item in a single row, we've joined those into one big string, now let's print that string out. So we'll say print output. So now for each one of the inner lists, we'll make a brand new variable, We'll traverse that inner list, adding all the individual items to that output variable, and then we'll print it out. And in fact, for good measure, just so we can see, we'll put tabs between each item, just so when we print these out, they're separated. Save, run our code, and there we go. We get the grid pattern we're looking for. 1, 2, 3, then a new line, 4, 5, 6, and 7, 8 after that. So a way of looking at this is we have 2 dimensions in our list, so we need 2 dimensions in our loops. The inner loop, let's say all of this, is more or less what we would do if we wanted to operate on a single flat one-dimensional list. And the outer loop just says, do that for every one of my sublists. Do that for each row. Now in this case, we solved it using regular for loops, but it might help people to understand if we see this using for each loops instead. So even though this does the exact same thing, let's solve this in a slightly different way. So I'll say print 2D list number 2. So this is going to do the exact same work, just with a different style of coding. So instead of using for loops with indices, we'll just do for each loops. So in this case, we'll say for each sublist in our input list. We'll take some output variable, and then for each one of the items in that sublist, so for Ellie in sublist, output plus equals the string of Ellie plus a tab. Print output, and we're done. So notice these do the exact same thing. The only reason I want to show this is that it might help you visualize or understand a bit better what's going on inside these loops. So the outer loop is iterating across the input list, the 2-dimensional input list. And the items considered in that loop traversal are themselves whole lists. We call them sublist here, and then we have our inner loop, which says for each element in our sublist, then we'll operate on those individual elements. Notice outside of this loop, we don't have access to those individual elements. We'd have to say sublist at some specific index, or we can traverse them as we've done. All right, let's save and test this out. And like predicted, it works the same. So traversing and printing a 2D list wasn't too difficult. The next task says build a multiplication table using a 2D list. So write a function that takes a number n as an argument and returns a 2D list containing the multiplication table from 0 to n inclusive. So if we said mult table at 3, this would return a 2D list where the entries in that list correspond to what they would be in a 2-dimensional multiplication table. So notice that first row is all zeros because the first value would be 0. The second row is all the multiples of 1, the next the multiples of 2, the next the multiples of 3. Okay, so let's see if we can't solve this. Returning to our code, we now need to create a function that creates 2-dimensional lists. So this function is called def mult table, and this takes in some integer that tells us how big the problem is. So we'll call that n. Now, to build a nested list, we're going to need a nested loop, as we've seen. We're going to need to make a loop that creates a single list which holds one row of values, and then we need to repeat that to create a list that holds all of those rows. So our overall result, we'll call that table, and that just starts as an empty list. And the things we store into that table will be the sublists that contain all of our numbers. So how many rows should we have in this table? Well, we need to go from 0 up to n. We want n to be included in this. So we'd say for I in range from 0 to n plus 1. So now every time through this loop, we're going to create some new row of values. So I'll create another variable here. I'll say row equals. That's an empty list. And now the rest of the body of this loop should fill this row variable with 1 row's worth of values. So that's all of the values from 0 to n multiplied by whatever the current row is. So if we're on row 0, we get a bunch of zeros. If we're on row 1, we get 0, 1, 2, 3. If we're on row 2, we get 0, 2, 4, 6. Okay, so we need another loop, so we'll say for j in range. And again, this one, it's a square table, so we'll say from 0 to n plus 1. And now inside this loop, we now have our row and our column value, our row value being I, and our column value being j. And all we need to do now is create the multiplication numbers themselves. And we want to store those in the current row. So I would say row.append, and then I just multiply those two numbers together, so I times j. So note if we're on the first row, I is 0. If we're on the first column, j is 0. We get 0 times 0 is 0. Then j goes up by 1, I will stay put, and we'll do 0 times everything. So we'll get a row of zeros. If we're on the next iteration, so I is 1, j starts at 0, so we get 0 times 1, which is 0. Then j goes up to 1, so we get 1 times 1, which is 1. And then j goes to 2, so we get 1 times 2, which is 2. 1 times 3, which is 3. And then we have a row 0, 1, 2, 3. Same thing happens when I is 2. We multiply those by j's. We get all the different multiples of j by 2. When I is 3, we get all the multiples of j by 3. For each one of those, at the end of this loop here, we're left with this row variable, a list that contains n plus 1 values. So if n is 3, we have 0, 1, 2, 3. Since this corresponds to one row from our table, all we need to do is add this into our table. So we'd say table.append the current row. Now once we're done this outer loop, table has appended all the existing rows, so all we need to do is return table. Let's try this out. So I'll say mult table 3, call mult table. Let's make sure we print the result. Python nestedlist.py, and we get our multiplication table. Now this might be a bit easier to see if I use our other function print 2D list on mult table, save and run again. And now it looks like a multiplication table, minus the headers. If we pass in a different value, so if we said mult table of 6, then we get a bigger multiplication table, again minus the headers. So our code seems to work. This is a fairly common pattern for building 2D grids. You might find it useful on your assignments and tests throughout the course and beyond. One thing I'd like to point out is that the way I've written this is a bit more expressive than perhaps it needs to be. We could write this in perhaps a slightly cleaner way by not using this row variable. This row variable here, it takes in a list, fills with values, and then we append it to the table. We could just be using the table the whole time. So what we could do instead of row equals a new list is say table.append a new list. And since we're on index I in our loop, we know that the new list we just added to table is at index I. So instead of saying row down here, we can say table at I dot append. And then we don't need this last line. Slightly cleaner, does exactly the same thing. We can save and run our code. We get the same result. So as we've seen, when we make a list variable, that variable itself is holding a reference to the actual list. But if we're storing a list of lists, then what we have is a reference to a list, which itself is containing a bunch of references to other lists. So in this case, we have a list called L1. That variable is a pointer to a list that has 2 elements, and each one of those lists has a bunch of strings in it, so ABC or XYZ. Right? Another way of thinking about this is if we had declared 2 independent lists, one that has the values ABC and one that has the values XYZ, then we could make a new list, called L1 in this case, that's just the list that holds those 2 lists. So we'd say L1 equals list1, comma list2. And we'd end up with a situation like this, a 2D list where the top level pointer is a pointer to a list that contains more pointers. Now in a previous video, we applied a function that would take one list and copy that list. So it would create a new instance of that list to prevent aliasing for flat one-dimensional lists. But what would happen if we used that same copy list function to copy a 2-dimensional list? Well, for nested list, this wouldn't be enough. So recall how the previous function worked. We had some list and we iterated across the elements of that list, making duplicates of those elements and storing them in a brand new list. And then we return that new list as the copy. If we did that here, what we get is a copy, a new list called L2, which points at a list that has 2 elements. But then when we go to copy those individual elements, so if we say L1 at 0 gets copied into L2 at 0, what we're copying is the pointers to the other lists. Right? So we're copying the addresses in that top level list, which themselves refer to the same nested list or the same sublist inside. So since the outer list is storing pointers to more lists, we're going to have to go one level deeper. We're going to have to follow those level pointers and then copy the individual elements over. So let's see this in Python. If we were to create a function that's called def copy 2D list, which takes in some list called L. And previously what we did is we had some result variable. We said result equals an empty list. And for each item in the range to the len of our list, what we had said before was result.append L at I. And then we returned result. So this copies a one-dimensional list. We traverse through each element and we say take a duplicate of that element and append it to this new list. But now since the elements that we're copying, this list at I, is itself a list, we have to go a step deeper. So instead of just appending it directly, we'll say inside that list, we'll make a new list. So we'll say row equals another new list. I'll say for j in range of the original list, so len l at I, we'll go through each element and append those. So we'll say row.append list at ij. Once we've done that, we can say result.append the row, and then return the result once we've done all the rows. So this is saying for each sublist of our outer list L now, we want to make a new list, and then for each one of those, this is saying for each item in that sublist, then we'll copy the item. So rather than copying this top level into our new list, which itself is just containing pointers, we'll go into that item and we'll grab the individual elements in that list and copy those instead. So let's test this out. We'll use some of our existing functions here. So let's say L1 equals mult table, and we'll do a small one at 5. And then we'll say L2 equals copy 2D list given L1. Now, if we want to know that these are different lists, that is to say if we haven't created any aliases, what we need to do is go into the individual elements and check. So I'm going to use some asserts here just to test that we're getting the things that we need. So I'll say assert that L1 at 0, so the first item in L, is not the same as L2 at 0, so the first item in L. We should also assert that L1 is not L2. We'd also like to know that L1 does equal L2. So let's test these out. So this first one says the top level pointers are not pointing to the same top level list. The second one says these two lists do still contain all the same values. And this third one says if we go one step further, if we go into one of those sublists, is that pointing at the same thing as if we go into one of those sublists for our copy? Notice if we go any deeper than that, we're looking at actual numbers. So if we save and run our code, this won't actually do anything. It's going to create a mult table, copy it, and then make 3 asserts. And if everything works correctly, this won't actually do anything. If it doesn't work correctly, we should get some assert errors and it'll crash. So let's bring up the terminal. Say python nestedlist.py, and everything works great. And if we want to make sure that the code's actually running, so we could say assert false, for example. And the code is actually running. Assert false will always be an assertion error. So it got through all those, and a success. Another way we can say that is at the end of this, say, all tests succeeded. Because we won't get to that line if any of these assertions fail. So if we run this, it says all tests succeeded, so that's great. So this copy 2D list does work if we have two-dimensional lists that we want to copy. It doesn't create aliases from them because it goes a step deeper to make sure. But note if we had 3 dimensions or more, this still would not be deep enough. Now there's no limit to the depth of nesting, so I could, for example, just open up Python here again, I could, if I want, create a 3-dimensional list. And notice I have 3 square brackets because there's 3 dimensions of nesting in this list. So the top level list contains all of the items here as the first item, and all of this as the second item. So the top level list should have a length of 2. Inside that first sublist, there are then 3 sublists. And inside each one of those, there are just 2 strings. Inside the second sublist, there are 1, 2, 3 sublists as well, and inside those, individual strings. If I press enter, I can say something like 3D list at 0, and that's the first item. If I say 3D list at 0, 0, and that's the first one of those, and if I say 3D list at 0, 0, 0, then that's the first of those items. So we have 3 levels of lists, so we have 3 indexes in order to get down to a specific item. Now technically you can nest these as deeply as you want, but if your solution involves very heavily nested lists, it's a good idea to reevaluate your design choices, as having heavily nested lists can very quickly lead to confusion in code, which is where errors start to creep in. And it's very often the case that a better design can simplify the nesting in your data structures.